we're going to start here, a week late, but, you know, a little problem with snow, you know about that. So I guess we'll roll right into it, start with Don here.
Sound okay? Welcome, I'm Don Stevens. I'm Director of Perkins Observatory. I guess I'm your cordial host for the meeting here. Unfortunately, we had to cancel last week because of the snow. It couldn't get the university to get out here and plow in time and that. So, but I apologize for that. And what we're going to try to do is make provision to move the meeting virtual in a situation like that again. So hopefully in the future, won't be so having to switch it off the second Saturday as usual. As I know some folks, they schedule around this. Speaking of schedules, we resume our public programs on Friday nights on January 31st. Those start at 8 p.m. And if you're looking for something to do on a Friday night, you want to help out, we can always use help with parking and pointing telescopes. And you don't need to be an expert, and you don't even have to have your own telescope. We've got telescopes here that you can use, and we'll pair you with somebody that is more experienced and can show the fine folks come to the program, Saturn, Venus, the moon, whatever happens to be up. And it's usually a lot of fun. Folks enjoy coming to the programs, and it's mostly because folks like you come and help out, so, and that is appreciated. I've not scheduled telescope workshops yet. I'm kind of just waiting to see what kind of interest there is. So if you have interest and you just got a telescope, want to learn the basics of how to use it and such, once I have enough people that are interested, I'll get that scheduled. We do charge for it. I'm going to do it as 2 sessions. It's going to be $90 for both sessions. So just reach out to me, and probably I'll shoot for like March or April, depending on the interest in it. So just fire me an email or give me a call here at the observatory and leave me a message, and happy to set that up. Other than that, I think that's pretty much all. Before I was doing one a month, I'll try to do them like spaced 2 weeks apart or something like that. So, and they usually run for about 2 hours.
Okay. So Joe has,
Yeah, we don't have any guests tonight.
okay, but go ahead with your,
We do have some events coming up for which we need some volunteers. The most recent one is a week from today at High Banks. We have several still signed up. I got a second sign-up sheet here for those who'd like to add their names. But that's from 5:30 to 7:30 at High Banks next Saturday. And then the next one coming up is February 6th, which is a Thursday evening. And it's from 5 to 7. And that's at Cranbrook Elementary School, which is just on the northwest side of Columbus.
If you want to, I can give some details.
Oh, yeah, go ahead,
Right.
yeah.
Yeah, that's the smaller elementary school on the northwest side off of Kenny Road, and my grandson's going, and so I have nothing to it. But they have it's a smaller school, but they have a lot of space outside. They have a little planetarium. They're going to use blow-up planetarium inside. So I told them the weather can be 1 out of 10 Fahrenheit or something, but they're going to have activities in any case. But if we could set up outside and show them the dramatic planet show that's we're getting right now, it will still be going then. And the moon, I think, they've got the whole thing. I brought a little chart there for. But anyway, so whoever can help out. It was one of the schools that the school board said, oh, we might close it because it's too small, even though their attendance was really good and their programs were good. And a local school, but they persuaded them, no, don't close it, so they're not going to at this point. But that's one reason the PTA is very active, like we want to show that this is a good school and that we're doing lots of stuff. And activities like this space night. They're going to do in the early evening a rocket launch at their big field behind it, kind of like Perkins does sometimes. And then second hour or so will be planetarium, and then we'll have our scopes out. And I looked on Stellarium, it's kind of dim twilight, but it'll be perfect for planets and the moon, so. And by 7, it should be done by 7, so you'll head out then.
So,
Okay.
pass these around, so this one over here, then, this one actually has 2 pages on it. The other one is coming up later, it's on May 9th. It's a sky viewing at Jeffrey Park in Bexley, and that's from 8:30 to 10. But if you are interested in helping with either of those events, please sign up, and give us your information. If you fill it out, you'll put your name in that, that's okay.
So, you got anything?
Yeah, I got a few things.
Okay.
Yeah, just so you guys know, the programs for at the John Glenn Astronomy Park start up on March 7th. That's the first Friday in March, and that's when we start going again. We, of course, don't do it like Perkins does. We actually do cancel in the event of cloudy skies. So if you sign up for one of those programs and want to attend them, I will send out an email that says whether or not it's going to go forward by noon on the day of the program, based on a judgment of the weather that day. As far as the Columbus Astronomical Society goes, we're thinking in March of doing a program that is about how to care and maintain your telescope. So if you know how to collimate a telescope or clean a mirror or add things to it and that sort of thing, we're all going to be getting our telescopes out for spring because the weather is going to start to get better. And I think that's a timely time to have everybody bring their telescopes, and we can get them collimated with laser collimators and figure out what they need and that sort of thing. So if you guys, any of you guys, Wilkie, want to help out with that, please reach out, or I will enlist your help for that. And next month, by popular acclaim of the board, I'm going to be doing a talk on special relativity. It's far simpler than you think, so that's going to be the February meeting. So, okay, and that's it. Okay. Oh, yeah. So this month we have back again. We had Sultana. You were in March, right? You were here in March because it was right before the eclipse. Yes. Yeah. So it was March of last year. She came and gave a talk on how to on her studies of iron in the atmosphere of the sun. This time around, she is giving a talk on a very different subject, which I'm anxious to find out about. I was just asking her, if you don't mind my saying, how you got into astronomy. Yes. And she said that her parents were very proud and they wanted her to go into medicine. And so as part of her studies, she started studying physics, got very interested in physics, and then picked up an astronomy book. And the astronomy book just blew her mind. And that's how she got into astronomy. And so now she's here at Ohio State University and giving us a lovely lecture tonight. So thank you so much for coming. I do appreciate it. So we're going to get you all hooked up here. And so that should...
Okay. Hello, everyone. I'm very pleased to come back and talk to you about lives not here, outside our Earth, and how also the study of exoplanets related to it. Okay. So we know our Earth is filled with intelligent beings. It starts, from human beings. So in the college, do you think this light can be turned off a little bit? So we think a lot. We know there are highly intelligent beings here. And then we also have animals on the land, also in the sea. And also we have microbes, and we have a lot of things in between where they are all intelligent. They know a lot of things. We know the most things, okay, as we know, all right? Sorry. So what happens, is it that, we are very unique, that we only the intelligent beings in the whole universe means us, or there's something else. The universe is very big, so this is a picture of the universe, a real picture of universe where each dot is a galaxy. But even though this picture has only very small fraction of total number of galaxies we have. Okay, out of 2 trillions, we have only 43,000 galaxies, and one dot you can think of our galaxy, which is Milky Way. Okay, so this is our Milky Way. Even though it is just one dot, but it also has 200 to 400 billion stars. And we are one of them only, and near the edge somewhere, not near the center. So the sun is our star. And then this sun has a bunch of planets. There are 8 of them, and there are also dwarf and other planets. And out of 8, we are here, the Earth. This is our home. This is us. So we can see that we're shrinking from the universe. We are just a tiny dot. Why it is not moving? Just hold a second. Okay. Now, I don't know how many people have seen this picture. It is called the pale blue dot. Okay. As a book written with this name by Carl Sagan. So this picture, actually, you can see this dot. That's actually our Earth. And this picture was taken by Voyager 2 at 4 billion miles from the Earth. So as it's passing through it, it took picture of the Earth. And then, so the question is that if there is a tiny dot or tiny dust in the whole universe, are we the unique that only all the intelligence being will be confined in this tiny dust, and the whole universe will not have any intelligence beings? So this question have been with us for a long time. Sorry. So, but the universe is so vast, so big that we cannot reach in other places to find out what's going on. So the picture was taken by Voyager. See, this is our sun, and if we have planets, this is just a picture of that you can say the solar system. So we have planets, and if you go, then we have Kuiper belt. So we have some dwarf planets around there. And beyond that, we have this, which is called Oort cloud, where we have this frozen materials, or you can say matter, and sometime in a small piece break off, and they become comets and go around the sun. So what happened? So Voyager, was at this point. This is the sun, and this is the Voyager 1 when it took the picture. And it has not even reached this cloud yet. It will take another 300 years to reach there. After that, it will take 40,000 years to reach our closest star, which is Alpha Centauri. Our closest star gives out light, which comes to our Earth in 4 years. So you can imagine the universe is so vast, even though we are just in a small, galaxy, but we are just so tiny, and we are claiming we are the most important people. That just doesn't sound correct. Okay. So we have been searching through terrestrial life. So how do we, before we didn't think about exoplanets or anything else. So we thought we can try to catch signals coming from outer space. So there was a program called Search for Extraterrestrial Intelligence, SETI, and it was actually a combination of US and Soviet Union that time. And there was this kind of telescope, radio telescopes were set up to catch all the signals are coming. But we have signals coming all the time. But we have to know which signals. Are they consistent, they show pattern, or they are just simple noise? So far they have collected a lot of signals. Only limited of them show some kind of pattern or some meaningful signal consistent, but nothing has confirmed any life form yet. But it is continuing giving its service collecting signals and studying the signals. And it thinks by 2040, it may be able to give some clue of life form outside Earth. All right? But in the meantime, we have our imagination. Our brain is always very active. So we create all kinds of aliens, and we have stories and a lot of movies, and we are very much Trekkies and things going on. So we have so we know what kind to expect. Actually, when we think, we are very logical, even though we are creating all these aliens, but we have reason why we create that kind of aliens. Okay, because we cannot go to them, so we imagine them, and then we make stories, and we think that they may be also searching for us. And then in the movies, we cannot go somewhere, so we have to create something called warp. We say warp 1, warp 2, when you see the movies, and they said warp means, so you are going in a space shuttle or Enterprise or something. So warp 1 means the front space, you squeezed it. So that means you, in a short time, you're crossing a lot of land or space, and the back one, you expand. So your back goes very quickly back. So you're pushed forward, and so that you can actually pass the speed of light. So those are called warp speed. Not only that, still now we cannot travel to many places, so we also created something called wormholes. So it's like in a hole, when you have the shortest distance to go from here to there, in the hole you just go quickly over there and meet those other aliens. Okay. So now to find out, to clue that what kind of, so these aliens actually, you will notice in the movies, they also have something similar to us. There's a reason for it. Why should they be similar to us? So on the Earth, so we try to find something called, through spectroscopy, the clue of life. Spectroscopy is a method you should keep in your brain all the time. One word. Sultana said once in spectroscopy. That means with spectroscopy, you can get so much information. Just remember, we can get a lot of information. So through spectroscopy, we try to find clue of life, okay? So this is like an atmosphere and on Earth. And if we look at the atmosphere through spectroscopy, we can find out what are the molecules or atoms exist in the atmosphere. Like we have oxygen, water, carbon dioxide. They are all related to living forms. Only thing you don't see here is something all of you know, is phosphorus. Okay? So phosphorus we cannot see here, we cannot detect it, but phosphorus is actually a basic element of life. If this is a DNA, we have carbon, nitrogen, oxygen. So these three elements are there. The red dot, that's phosphorus. Without phosphorus, we cannot survive. It is one thing that, that through which we have masses passing. So we did not see phosphorus in the atmosphere, but the reason for it, as phosphorus is very active, okay, just hold a second. Okay, so then we see that in the space, the elements that we find, all kinds of elements, and when we see them, we see that all those elements are in our body. That means we are made from star dust or the elements that are found in this space. So if we are made of all these elements, then all the aliens, other living forms, should be made of those elements too. We may not look like the same because of the environment or various things can be changed, but the aliens, we expect them to be similar to us, okay, in certain respect. So that's how we got, so this is a cartoon, I like this one. It was in New York Times, published in 2015. It says then our cosmic selves, and we have all kinds of dust that forming us. Only thing in this article mentioned that we have detected everything except phosphorus. So sometimes it says that it is the missing piece that we are not finding any living form outside our own Earth. Okay, So this is from another Sky Survey. Sky Survey, and there is this apogee project that OSU has. So we have various kinds of elements in our body. You can see the color. The red one is the phosphorus. So what this survey did, it went through all the wavelengths, and see this wavelength, each element is its own wavelength, so they are unique to the element. So when we survey, we find all kinds of elements, and in these wavelengths are telling us which are the wavelengths, and you can see only here this tiny bit phosphorus. We don't see much phosphorus in space either. Okay, so the phosphorus is something which is scarce, and maybe it is something which is hiding there, and we are not able to find it. So that's why we are not able to find the aliens wherever they are. Okay, so this is just phosphorus. It is very reactive element. It will interact with the surroundings, and so it forms a new compound. So it is not very easy to detect. Okay, and because has not been found in the space, it has not been studied much. So my focus, or the group actually largely led by me, so focus has been study phosphorus, give all information through spectroscopy so that we can find the clue where the life form we can expect to see. Okay, but strangely, phosphorus is abundant in our solar system. So much phosphorus. All the planets, we have a cycle. This is just the planet cycle. You can see phosphorus cycle is how it is going, everything. But it is not the same we find outside yet. But with the latest, you can say observators in space, we are finding phosphorus here and there. One is this, Cassiopeia supernova remnants here. You can see we find phosphorus in this supernova remnant. Okay, so phosphorus is there, and we are detecting more. All right, so we are hoping that some point we will find living form either in this micro form or very intelligent form. So time to time, there are claims we have found some kind of evidence, and everyone becomes very excited. So I'll give you two examples. One example is this rock. It fell. It actually started from Mars, and somehow it was ejected, because of the motion, and it started to travel, and it fell on Earth in Antarctica. Okay, so in 1980, but then it was studied and tried to find what is inside, and because this kind of rock is not found on Earth, and so they call basalt rock. But this kind of basalt is all forming on the Mars. So we knew that it came from Mars. But inside, we found carbon fossil. And it was very exciting news. That means Mars has at least microbes. So that's why the fossil formed. But then further study showed that form, it is so much uncertain that some kind of carbon may have seeped in when the rock was forming, maybe a layer of carbon was there, and put a deposit of layer or somewhere there, and so we could not be conclusive that Mars had any kind of microbes. But it was a big news. The other news was more recent. Actually, everyone got very much excited. So they say, this was the title in the news, is alien life living in the clouds of Venus. And Venus is right, they say they found phosphine in the atmosphere of Venus. So this is the phosphorus spectrum coming from spectroscopy. So spectrum usually gives lines. And all these lines, remember, spectroscopy means the lines formed because of the photons, which is the unit of light, either being absorbed or being emitted. And they form this kind of lines. Today you are going to learn how these lines form because you are here with a physicist. All right, so the Venus, this is the Venus, but we know that it is very hostile to living form because on the surface, the temperature is 900 degrees and density, much 90 times more than the dense, thicker than atmosphere we have. Not in that it is carbon dioxide and sulfuric acid. So there could not be any living form on the surface, so they cannot surface up on the atmosphere. So this is the controversy. So but they say we found very distinct line of phosphine, but it could be a little bit, make up things too. So then there was we did see phosphine, but there was some explanation for this, saying that like this is our Earth. Phosphine is seen in our Earth because we have a lot of phosphorus. So this the outermost layer we call it ionosphere. This sometimes the element here they just surface up with the atmosphere upper layer here. So in the upper layer is the one where from outside we can see things, take the spectrum and do the spectroscopy to find out information. So and it has been found that microbes sometimes can be seen high up in the atmosphere, and phosphine could be here. So it says like either solar flare or maybe a comet when passing through the Earth, it grazed through our atmosphere and also through the Venus atmosphere and deposited some phosphine there, and that's how we detected it. So there's no way that phosphine was created or originated Venus itself. Excitement, even we were very much excited and started to show this picture to everyone. All right. Now this experiment, now the research on this life form, there's a boost up after we discovered exoplanets. So again, like our sun has so many planets, why not the other stars should have planets? The question was there, and they assume there should be more planets, but there's no evidence. Until 1988 or something, there was something in a constellation from the motion they could say that something is there, maybe a planet is there. And then there are some more evidences in 1992. The first direct evidence of an exoplanet was seen in 2004, this one. This is the first one, and it was taken from the Earth. The telescope is up in the mountain in Chile, and they took this picture. So then it was the direct proof that planets exist in other stars too. So these ones, we don't call them planets, we call them exoplanets. Then we have started to discover many exoplanets, so we have to have special kind of observatories. We even discovered, like our Earth has 7 or 8 planets, and this one also has, I think, 7 planets, TRAPPIST-1. So we are recording, and I think the last number I saw is right now 5,811 exoplanets that we have found with confirmation. All right. Now these exoplanets have to give. There are so many exoplanets, so you have to find some way to name them. So the way we do it, and now if we say exoplanets, so say this is star. Okay, it has a bunch of exoplanets. So say one telescope, say a TRAPPIST, found this star, so we call it TRAPPIST-A. And all the planets will be called TRAPPIST B, C, D, or whatever number of planets this one has. I wanted to show this picture because the way it is not very easy to detect planets, because planets don't have light coming out. We can see objects, only those objects which can give out photons and reach our eyes or telescope, only then we can see those objects. So what they did, the US astronomers thought about somehow we have to block the light around this star, so then we can see this planet. So we found this star, the host star with a bunch of planets. Okay, now there's an interesting number that I thought you'd be interested to know. So far we have found 5,800, but if we think our galaxy has about 200 billion stars, and they're not all the stars we expect to have planets, but particular ones probably. But most of them should have, at least we should have 40 billion exoplanets going around the host stars. So we should have 40 billion, and out of that, we are more interested one kind of exoplanets, which are habitable exoplanets, and we expect that to be at least 11 billion exoplanets. That means we can go to many homes, almost 11 billion. Only thing is that you have to find a way to go there, and we have to find where they are located. All right. So there are a bunch of observatories which are just searching for these exoplanets. The main one is this Kepler. Right now it has retired, but it has detected largest number of exoplanets, and this is the one. TESS is the more updated version of this Kepler. So the Kepler has detected so many exoplanets, and they are like classified here. So we keep on detecting, I'll tell you, and not only that, it can, from the spectroscopy, it can tell even the size, temperature, or a number of information. So what we do, okay, there are several ways that we can detect the exoplanets. I'll just tell you only the most common one, and it's the easy one to understand. So let's say, for example, this is a star, and it has a planet. So this planet is going around it, or exoplanet, going around it. So what we do, we focus to this star with a telescope. Each telescope has certain wavelength that it can detect. Okay. So this is for example, this is the certain wavelength it can detect. It is focusing on it, and then at certain point, when this planet is going around it, it is blocking part of the light. So we see a dip here, less light. So then from this we can tell, this the wavelength in this region. So this is the planet, and from this we can get a lot of information. What is happening? The light from this star is passing through the atmosphere of the planet, and that light. So we have some light. So it is going through the atmosphere. So it is illuminating the atmosphere, so we can get the picture of it, and then we can do the spectroscopy, and not in that we can find out a lot of information of this exoplanet. So this is called the transit method. There are a few other methods being used, and we have detected many of them, but the transit method is the one which has detected most of the exoplanets. All right. So after finding them, then we have to categorize them, and we are very much interested in the habitable planets, but we have to study all of them. So I don't know how many of you have studied astronomy. There's something called HR diagram. That means if we know the temperature and the intensity of the light, the flux coming out, we can put them in a diagram, and they look like this. This is called HR diagram. Okay, so there are many stars fall into this category. So we need, and there also we found new categories too on the side, these three, but this is the main one, main sequence one. And we found that all these planets. So if we classify them, that we see that the stars which are called GKF. How many people know about these words? OBA. Can you raise hand? Okay. So who don't know, remember the stars are classified OBA. So the students say something, so it is easy to remember. Oh, be a nice girl and kiss me. Okay. So these stars, we found that these stars have planets which have the possibility having a habitable planet. So which are habitable planet? That means it has to have rocky surface so that we can walk. It has to have water, oxygen, and also it has to be a little bit far away from the star itself If you're too close to the star, that means all kinds of bad radiation cause problem. Well, he knows about it. He told me he's a radiologist. So we want to be a little bit away from the host star. So it just turns out that these are the types of stars which can have habitable planets. All right? So now we are very lucky. The reason we are lucky, our nearest star, which is 4 light years away, has one habitable planet. And that's where we have to go. Actually, we don't have choice. We really have to go in future. If we want to continue human race, we really have to go there. So this is our sun, and the nearest one, there are actually 2 stars. We used to think they're just 1 star because they're far away, but it seems Alpha Centauri has 2 stars. It's a binary stars. And then recently we found it has a planet too, and that planet is a rocky one, and it is a habitable one. So we are very lucky. We don't have to go far away. If we can somehow reach there, then we have a home, another home, after our sun dies. Okay? So these are just showing the size of it. But from here to go there, I told you Voyager, it will still take 40,000 years to reach to this Alpha Centauri right here, where the Voyager is going. But if we have better technology, with the current technology, if we start from the Earth, we'll still need 18,000 years to reach there. That means we have to have generation going coming to reach there. But we can't do that, right? So but our brain is always active. We think about how we can reach there. If we can send a probe there, that means basically we have reached there. Now we have to find other ways how to go there physically. So there are ideas like you have a probe, and you put it in like a spaceship, and which will be traveling at the 1/4 speed of light. If we have some laser pushing it, and it is going at that 1/4 speed of light, it can reach there in 20 years, within a lifetime. All right? So, but we need to develop that technology. We are still far, far away from that technology. So we need more people in STEM. Is it worth it? Yes, of course, because our sun is going to die, right? And it will become a red giant after 6-7 billion years. Don't think 6-7 billion is far away. So how long have you been here on this earth? Dinosaurs died 65 million years ago. And we came probably, I don't know, maybe 60 or 50 million years ago. And so far, what we have done, we can go up to Moon or Mars. So after so long, if it takes so long to go to that far, that means we will take long time to reach the other star. So that means this time is not a very long time. It is still a kind of short time, so we have to make progress faster. All right? So the sun ultimately will become like this big. That means with all the planets will be inside, and there will be no light, no light created, the sun. So all this fuel, which is the hydrogen, will be gone by that time. Everything will cool off, and all of us will die. And with our brain sitting there, we cannot let us die. We have to continue and live. Okay, so that's why we have right now one of the finest telescope out there, which is JWST, James Webb Space Telescope, and out there is far away from the sun. This is the farthest observatory, you can say. The reason is that this is very sensitive. This you can say the panel which is collecting the photons, and this is all gold. And it is so sensitive. Our purpose is to collect the weakest kind of photons that is traveling. Because the weakest kind of photon means it is started long ago, maybe from Big Bang time. So it is traveling, and with time it has become stretched. The photon becomes stretching, means the wavelength is stretching. That means it becomes weaker and weaker, and we want to detect it. And so this with gold foil, it has good reflectivity. So whenever a very, very weak photon just hits it, it bounces back here, and then photon and take the image and it goes to the spectroscopy to analyze that photon. Okay? So there are two main purposes for this JWST telescope. One is to go back in time to find out Big Bang, how it started, what happened in Big Bang. The second one is find out the extraterrestrial life, how the life started and whether there is any other life form outside our Earth. Okay? Strangely, it has been serving very well for us. It found water. It found, say, in one of these exoplanet called WASP. It is far, far away, and it, again, it is a spectroscopy. So the photons are coming, and it is collected, all these photons. So when you plot them, it looks like that. When you match it with water spectrum, and you see these are all water lines. So that even though in the very, very in the past, the exoplanets were created, and some of those exoplanets had water. So this is the proof. So this is a very good information for us. So the ones we are on Earth, so we're studying this and try to find out how to explain it theoretically. So we do mathematical understanding. I don't know whether because of the light you see that, but the picture you saw, so we try to simulate it. This is our group picture here for the similar kind of spectrum. Not only that, before JWST, we did find water on one of the exoplanets, and they are here. There are three. Those are like we found at these energies, the water. We identified those photons belong to water, and these are the spectrum. So water they studied. Someone named Jonathan. Okay, so he all his life, he studied largely water. So he has a huge data bank of water lines, and so they have been modeled and found that they match with this model. So this is the proof that the water exists in that exoplanet. So this is our group picture. So we are seeing this kind of model. So we are trying to simulate this kind of models too. So just showing that we are also working on this model and try to find various things, particularly some clue of life outside the Earth. And this is another one, beautiful picture, and from JWST, an early one. So this picture you can see, it came from a galaxy which is 13.1 billion years away from us. Okay, so the photons from that galaxy have been traveling, and they were caught by JWST. And then when we caught these photons, these are the lines we saw. So these lines belong to what? Photons. I'm going to discuss about it next. So these lines we found, and we matched these lines, and we found that oxygen, hydrogen, and neon, those elements form. And we did not know that these elements formed so early on. We used to think at that time about the universe is 13.7 billion years old. And this one, is still kind of close to that. We used to think, these kind of elements form up beyond that, much after this. But this is the new information we are finding. The main thing is that, mind-boggling is that these photons, which started 13.1 billion years, have been traveling for this long time until they were caught by JWST. What do you think about it? These photons have been traveling on this space for such a long time, And then being caught, then we found out about them, we found out about this galaxy, and now we have more information. I thought it's very beautiful. Okay, now since you are here and you see all these lines, so whenever you see these kind of lines, what we have to think again? Oh, they came from atom because atom took some photon and got excited. So if it is excited, the line is usually dark. Okay, when the photon comes out, it goes down, you have a color to it. Photon coming out means the photon is actually coming out, so we see the photon, and each photon has a color. And if the photon is absorbed, the line is still there, but it is absorbed, so you don't see the color. So now how these lines form and how we identify, that's what I'm going to tell. Okay, now this is an atom, and we have electrons going around. This is not very ideal picture of an atom. So this is the nucleus. Nucleus is what? Okay, not you. Nucleus is, what are the, do you know nucleus is made of what? Yes, protons and neutrons. Okay, and the electrons move around. But these electrons move around not randomly, they are all quantized. That means they have fixed orbit. Okay, this is what brings a lot of advantage for us because they are quantized. That means they are fixed orbit and fixed energy. So if one electron wants to go from one orbit to another orbit, it needs that much energy to go up there or give out that much energy to go down. And we know about it because they are all quantized. They are not random. Nature is very, very consistent, very disciplined. Okay? So because they are quantized, we can tell for each element, each atom, what will be the energies. So energies we write like lines like that. Okay? It is 0 energy or say 5 keV or 10 keV like that. So there are many, many energy levels for each atom. But this spacing, they are all different for different species. So this set of energy levels are unique to a particular atom or ion molecule. So these arrows are showing, if we excite electron from this energy to say that energy, it is another quantum orbit. It goes there, then it comes down. So one thing is that nothing can remain excited for a long time, even these electrons. So they go to excited state. There's a lifetime for the excited state. After that, it comes down. To come down, it has to shade out the extra energy. That extra energy comes out as a photon and forms a line. So these are the lines it forms. So the lines are always there, still in front of you, and all of us are lines in front of us, but we don't see them because all of them are together. All these photons together, we don't see them separate. But if we can separate them, we can detect all the photons that the light consists of. So there are two ways usually we do spectroscopy, you can say. One is like, say this is a prism, say white light is going, this one and we can see that there's all kinds of color come out. Why? Because all these photons were here, but when they're passing through the prism, each photon has its own direction and angle, which way it would like to go. So because of the medium, so we know that photons, they go at different angles, so that means we can separate them out. The same thing, you see rainbow, so you see water molecules in the atmosphere. The sunlight is coming, and this atmosphere with the water molecule, it acts like a prism. So when light is passing through it, so this prism, this all together, separating out all the photons into different angles. So we see a rainbow. So other way that we see, which is more common to do a spectroscopy, instead of sending it through a medium, we can send the light through a slit. Just a slit. When the light goes through it, again, there's a diffraction. It's nature of light to diffract. So when it diffracts, it also will depend on the kind of photon or wavelength we have. So when it's going through it, the photon will go at different angle, diffract. And so that time with the spectrum will look like this. So we are separating out all the photons. They are all together, we don't see them, but if we pass them through a diffraction grating or a slit, and we can separate out these photons. So this is actually most common. This is the spectroscopy. That means we are separating out all its colors or all the photons, and then we match these photons with the known numbers. We study this. So see, we see a spectrum from JWST, the line. So one of the lines we see, it's a nitrogen. So I say with that nitrogen, what we do, we compare the energy with these lines. Oh, this is for carbon. So we'll see that, no, it is not matching with carbon. So it is not a carbon. So then we go to nitrogen. So nitrogen, and then we see energy, match the energies, that energy with the energies of the spectrum. And then if they match, we say, oh, it is nitrogen. That's how we do spectroscopy. We can detect or we can identify the elements contained in a particular kind of light. Okay, so there are two kinds of photons, and I will just discuss. They form line. One is, I just said, this is the energy levels for a particular orbit, and this is energy, excited energy for another orbit. So photon is coming, electron goes from here to there. Usually only one electron jumps up, jump down, but sometimes 2 electrons do that, and once in a while 3 electrons do that. Okay. Depending on the energy of the photon, we can have 1 electron jump or 2 electrons or 3 electrons. So typically it is only 1 electron. So jump up and down. So we calculate some quantity. Okay. So we describe the atom itself by a mathematical expression. Okay. We describe, and then we calculate the probability of jump up and jump down. So then the sub, or you can say field, where we can calculate that is called quantum mechanics. Okay, because quantized, the levels are quantized, so they go up and down, they're quantized, and the whole study is called quantum mechanics. Okay, so we calculate one, so this kind of jump form lines. So, but this jump means electron still remains attached to the atom. It can jump up and then it will jump down. Okay, so that means we call it bound. Now, electron remains bound to the atom. So, and they form lot of lines because there are many. All right. So, we have just too many updates, and sometimes it's so annoying. So, and if we, and if you don't, update, then it will start giving messages. You did not update your system. So anyway, okay. So so this is for phosphorus, because I'm studying phosphorus. This is the lines are made from phosphorus one. You can see that all this line, both pictures have the lines for phosphorus. So when you have all this kind of transitions, electron going up or down, it's the same thing. Between two, if there are two energy levels are the same, up and down have the same probability, then you can have this kind of lines. So you can see many lines you can see, and the strong ones. So whenever we see spectrum, we try to see, maybe the strong ones will be visible, because these are these are showing the strength of the lines, and there are a number of lines. So we know that this at this wavelength we don't have many lines. Maybe they will be visible in the spectrum. Okay. So this is one study. The other thing that I would like to mention that you should know, the electrons. See, this is we call another process called photoionization. See, this is the atom and electron. It's the same. Electrons are moving, and the photons are traveling. It can absorb the photon and go to an excited state and form those lines. Okay, can absorb or emit. But what will happen if the photon energy is high enough? This electron becomes too energetic, and it cannot stay with this atom anymore. So it will leave this atom, which we call ionization. Okay, so this is called ionization. The electron is leaving. If we do that, then the lines are different. study is different, and the process is called photoionization. And the thing, kind of line you see is like this. I just wanted to make you familiar. So this is kind of lines you see, but this is from experiment. And this experiment was done in this setup, synchrotron setup at this Lawrence Berkeley National Lab at University of California, Berkeley. So this is the spectrum they got for phosphorus 2, another ion of phosphorus. And after, my colleague or my collaborator, so he sent me this picture. Okay, this is the spectrum we see due to photoionization. Okay, now they cannot explain it. So then you need theory. You have to go through the underlying science and find out what is this kind of a spectrum. So next then we'll show what I did. My collaborator. So this is what he sent me. Then I studied phosphorus, and for that particular kind of atomic process, and then what thing our group does, very accurate calculations. We are known for that we use the most accurate method, try to get the accurate numbers, and that's why we use supercomputer a lot. So OSU, Ohio Supercomputer Center, gives us a lot of time, and they are extremely generous with us. But anyway, so we see that after then, I find that for various states, the features, these features don't belong to a particular state. Electron can be excited to various states, and then the particular. So I'm calculating all the states, how they look like when they excited to a different states. And when I combine all of them, then it will look like this. So you can say that you can explain this feature coming from here, this feature coming from there. So this is how we explain. But this is the theory, and that's the experiment. Yeah, but experiment, theory is very exact, but so you can see, they are more like broad in. Because we have detector. Detector doesn't have very fine wavelength to measure. It has certain width, so it will be broad in. It has other field, other external field working on that. So you cannot get very sharp lines. But whatever you see, that's the real thing, you see. That is the advantage of experiment. And whatever you see, these are, and theory is just exactly what are the energies that I'm using, and so this is what I'm seeing. Okay, so this is a proof that whatever you see in experiment can be explained. So our purpose is to calculate, those kind of more quantities, more of them. Then what we'll do, this is already done. This picture was actually plotted by one student, Michael Rothman. He has moved to University of Colorado, but he plotted this, the atmosphere, our atmosphere, and taking what I did, but someone else did, not mine from. So he, a different kind of data, and he plotted how our atmosphere looked like, These various photons are making this kind of spectrum. These photons belong to water or sodium or magnesium and all kinds of things. So what we plan to do after we calculate all this phosphorus, add those photons in this spectrum and see how it looks like. Because our Earth's atmosphere looks like that, so we hope that, sorry, exoplanets, if they is habitable, maybe look like similar to us. At least we can put the standard for it, and then we can, whenever you see the spectrum, we can compare and understand, explain. Okay, that is all I wanted to say. I just want to show this is the book that my colleague and myself wrote. It has all the basic physics and astronomy. Thank you.
So phosphorus is, why is that a life molecule? I mean, wouldn't phosphorus appear in nature without life? I mean, obviously it's in the universe, it's manufactured by stars and that sort of thing. What particular qualities makes phosphorus a particularly good element to look for the spectra?
Okay, so first, the interest phosphorus is that it is a basic element of life. And we haven't seen phosphorus much in the space. We haven't seen any life in the space. So maybe it is a missing link. Whenever we find phosphorus, maybe the life form will be there. So that is what we're assuming. But not necessarily. Okay, there may be life form without phosphorus, but we know that phosphorus is essential, like DNA-based life form, like us. And second thing is that even though we did not find phosphorus, doesn't mean they don't exist. We are not just able to detect them. Okay, so with a finer, kind of special kind of telescope, we should be able to detect them more. Actually, we are detecting more now. And maybe we'll be able to detect, in some exoplanet. And if we know, we can be almost definite, maybe there's some life form in that planet. So that's the interest. You will not forget phosphorus from now on.
Yeah, no. So the transit method of studying the atmosphere, the planet is obviously extremely small relative to the star. And the amount of light that is passing through the atmosphere occupies a smaller area still. I mean,
Yes.
A very small area relative to the star.
It's very difficult.
Yeah, and so the star itself is going to have a very complicated spectra. I mean, it's going to have various elements in it, and its spectra is going to be very noisy because there's a lot of stuff going on, a lot of movement in the atmosphere of the star. What technical difficulties do you have to overcome to subtract out the light of the star and leave behind just the light that passes through the atmosphere in order to do this spectrum?
Okay, actually, it's a very natural question. But when the light is passing through the photons, they say oxygen photons probably will absorb oxygen. So whatever light actually, even though star has its own elements, but the light is causing the elements in the atmosphere, exoplanet atmosphere, excite. So we are, what we're seeing, so we are assuming what we're seeing, they are from the atmosphere of the planet, because we are using the light to excite them, and they are the one which forming the lines for us.
So it's actually the effect on the elements in the atmosphere that you're studying, and not
the elements in the star. We are using the light to excite. See, the photon I just showed, the phosphorus, the photon being absorbed by, say, oxygen of that exoplanet, it will be excited and come down, and it will, the photon, and that's the photon will form a line for us.
So it's not a transmission spectrum, it's an emission spectrum.
If it is a photon coming out, it's emission, but even when it is absorbed, we still see a line, it will be a dark line.
Okay, so it is a transmission spectrum. So
Yeah, so, okay, now the plot I just showed, the figure, this is an absorption for the atmosphere. When you see, this is the, like if all the lines looks like below, some, we call it continuum, the background. If the lines are below the background, we call them absorption, because usually they are absorption lines. And if they are above, we call them emission. But they have colors, emission ones, but not the absorption ones.
it just, what I'm curious about is, though, you have to have a very good model of the spectra of the star to begin with.
What they do.
You have to track out the star's spectra in order to see what's left behind, right?
Yeah, what you do is you take the spectrum with the planet in front of the star,
Yeah.
and then when it's in eclipse, the planet's in eclipse behind the star, you take the spectrum of the star
Subtract
itself,
the two.
and then subtract that, and then what's left over
Yeah.
is the planet's spectrum.
That's what I assumed, and I just assumed that it involved extreme technical difficulty because the amount of noise
It's,
is
yes.
incredible.
Yes, and it's very faint, and it's very difficult, but that's how it is right now.
Okay,
Yeah.
so James Webb is able to do it pretty well.
Oh, yes, it detected water
Yeah.
and in that exoplanets. Because it can detect the weakest kind of photons. So no other telescope can do that, which it can do. This one? This is, yes, our atmosphere. This is actually theoretical. Yes, we can. But there are so many lines, experiment usually, it is limited. But with theory, you can calculate a lot of levels. So, yes, but I would say experiment we can do some and compare isolated lines.
What I'm going on with this, it's like, well, for the exoplanets, we're doing this from very far away, so it's a very faint signal. I wonder if there's a way to sort of like add enough noise to experiment a little more that it signal. So then you see if you can detect phosphorus in our own planet, because we know it's there. Is anything like that done?
Whenever there's a spectrum, you measure and from the space, it has a lot of noise always. Then there are programs, IRS and various program. All the spectrum. This is the details. You don't see that part. Go through that program, and the program, from the nature of the lines, it can tell this is a noise. This is not a real line. The cleanup. And then we look at the cleanup picture because it deletes, take out the noise. The programs like it. Almost all spectrum go through, this, yes. Yes.
Thank you.
You're welcome.
I just had an announcement real quick. There's a lot of carryover between the fields of atmospheric science, meteorology, and astronomy. And I've been working with a group of folks to put together a local chapter of the American Meteorological Society in the Columbus area. Our inaugural meetings will be held on Tuesday over at the north side branch of the Columbus Metropolitan Library near OSU's campus. All of our meetings moving forward are going to have both an in-person and a virtual component. So if anybody in here takes a fascination with weather and would like to know a little bit more about that, just come see me after the meeting and I can talk a little bit more about that. Thanks, Charles.
Yeah, speaking of virtual meetings, what we're going to do is we're going to put together an option for if we run into a situation like we did last week where we get snowed out basically, that we'll be able to have some form of virtual